We have just discussed the advantages and limitations of thin film silicon solar cells. In this video we will discuss a material that is crucial for this type of solar cells, namely amorphous silicon. We will learn what amorphous silicon is and how it is different from crystalline silicon. To that end, we will discuss the defects in amorphous silicon and how they affect its important material properties like the conductivity, bandgap energy and absorption. This video shows an amorphous structure being built up bond by bond. You can see, as the figure builds up further, that it's hard to find any order in this network, and you are correct. This figure shows a so-called continuous random network. On atomic length scales, or what is called short-range order, the atoms still have a tetrahedral coordination structure, just like crystalline silicon. But the silicon bond angles and the silicon bond lengths are slightly distorted with respect to a crystalline silicon network. Therefore, at long-range orders, the lattice is no longer like crystalline silicon lattice. Single crystalline silicon consists of a perfect crystalline lattice, with each silicon atoms back bonded to 4 other silicon atoms. Amorphous silicon is a continuous random network with no long-range order to be found. Therefore, not all silicon atoms have 4 silicon neighbors. If we look at these structures in 2 dimensions, we can discern the different types of imperfections that occur in the amorphous silicon lattice. The gray circles are the silicon atoms, and the lines connecting them are the covalent bonds. Since silicon has 4 valence electrons and the lattice is random, some valence bonds are not connected to other silicon atoms. These bonds are known as dangling bonds and are indicated by the red lines in the lattice. The dangling bonds are in fact defects, and consequently amorphous silicon has a much higher defect density of around 10 to the power 19th per cubic centimeter compared to, for instance, crystalline silicon, which has about 10 to the power 12 to 14 defects per cubic centimeter. The defects lead to fast recombination of photoexcited charge carriers and cause amorphous silicon to have a poor conductivity in reference to crystalline silicon. Therefore, amorphous silicon is hydrogenated. The small hydrogen atoms attach to the dangling bond, thereby passivating the defect. A hydrogen passivated dangling bond is indicated by the small white circle on the end of the dangling bond. A hydrogen passivated material is indicated by the addition of colon H to the abbreviation. Often, however, the term hydrogenated is left out for simplicity. The hydrogen treatment reduces the defect density in amorphous silicon films by about 3 orders of magnitude. Defects can also be purposefully introduced in the amorphous silicon lattice in the form of P or N-type doping. The dangling bonds are not distributed homogeneously throughout the amorphous lattice. They rather tend to group in small clusters. They can thereby form a number of typical defects such as monovacancies, divacancies and nanosite voids with a diameter of several nanometers, which surfaces are mainly covered with monohydrides. In these nano-sized voids, it can even occur that a silicon atom at the surface has only 2 bonds with neighboring silicon atoms. The 2 dangling bonds are passivated by 2 hydrogen atoms. Such silicon atoms passivated by 2 hydrogen atoms are called dihydrides. But how does the amorphous structure affect the material properties of the silicon lattice? To answer that question, we will first look at the band diagram. As you may recall, the band diagram visualizes the energy levels of electrons in a semiconductor material. As explained in the PV energy conversion course, electrons are allowed discrete energy levels as described by the Schrödinger's equation. This arrow is an axis indicating the direction of increasing energy level. At the lower end of this axis are the various allowed energy levels of the valence electrons that are bound in the silicon lattice. These levels are in the valence band with the upper energy limit known as the valence band edge, indicated by EV. The energy levels of the unbound or conduction electrons are represented by the conduction band. The lower energy limit of the conduction band is known as the conduction band edge, as indicated by EC. The energy levels between the valence and conduction band are in the band gap, with the band gap energy defined as the difference between the conduction band edge and the valence band edge. For convenience sake, we will rotate the band diagram figure to look at the density of states function of crystalline and amorphous silicon. The density of energy states, or density of states, which we denote as G, is an important parameter that tells us the number of allowed energy states per unit volume as a function of energy. So it basically gives the density of a certain energy level or state in a semiconductor material. We introduce an axis for the density of states on the right-hand side, while the x-axis now represents the energy level. The density of states of valence electrons in the crystalline silicon is indicated by this curve. The density of states of the conduction electrons look quite similar. We can see that as we move further from the edges of the bands, more energy states are available. Crystalline silicon, with its well-ordered structure, has a well-defined band gap with an energy of about 1.1 electron volt. The amorphous silicon lattice is random. The different types of defects and types of vacancies lead to a larger range of allowed energy states that are not allowed in the crystalline lattice. The density of states of valence electrons of the hydrogenated amorphous silicon therefore looks like this. Again, it's quite similar for the conduction electrons. These extensions of the conduction and valence band edge are known as the band tails or Urbach tails. In addition, the defect states in the amorphous silicon create allowed energy states in the middle of the forbidden gap. The absence of well-defined band edges makes it difficult to define a band gap energy for amorphous silicon. Empirically, however, we find that an optical band gap can still be defined. This band gap is also known as the mobility gap, which extends between the top of the band tail edges. The optical band gap of amorphous silicon ranges from 1.6 to about 1.8 electron volts depending on the hydrogen content. Due to the greater number of allowed energy states, the electron momentum of amorphous silicon is poorly defined. Amorphous silicon is therefore a direct band gap material, and amorphous silicon has a larger band gap than crystalline silicon. Let's see how these properties of silicon affect its absorptive behavior. We put the density of states near the band edges of crystalline and amorphous silicon to the side for reference and introduce an x-axis indicating the energy of incident photons. The y-axis shows the absorption coefficient alpha. Since the photon energy and wavelength are inversely related, we can introduce a second x-axis on the top of the chart, displaying the wavelength. We now plot the absorption curves for crystalline and amorphous silicon. Crystalline silicon starts absorbing from its band gap energy of 1.1 electron volt, and initially, just like the density of state, near the band gap, the absorption increases exponentially from this point. This can be understood by realizing that the low density of energy states near the band edges means that photons with an energy level just above the band gap energy have a low probability of exciting an electron from the valence to the conduction band. As the photon energy increases, both the number of valence electrons capable of making this transition increases as well. Due to the defect states and band tails of amorphous silicon, electrons can already be excited to the conduction band at very low photon energies. It already starts absorbing from very low energy levels. Again, the initial shape of the absorption coefficient curve corresponds with the density of state curves. Starting from 1.8 electron volts, the absorption coefficient of amorphous silicon becomes at least an order of magnitude larger than of crystalline silicon due to the direct band gap. This means that in the visible and ultraviolet part of the spectrum, which are the parts with the highest photon energy, amorphous silicon is much more absorbing than crystalline silicon. This makes it such an interesting material for thin film solar cells. Time for a short recap. We have discussed how crystalline silicon consists of a well-ordered lattice, while amorphous silicon consists of a continuous random network. This random network causes amorphous silicon to have a much higher defect density. We also saw how these defects create allowed energy states in the bandgap. Amorphous silicon therefore has a direct bandgap of between 1.6 and 1.8 electron volt, while crystalline silicon has an indirect bandgap of 1.1 electron volts. Finally, we saw how the direct bandgap of amorphous silicon leads to much higher absorption of about an order of magnitude in the visible and ultraviolet parts of the spectrum. In the next video, we will discuss an important consequence of amorphous silicon for the device structure of a thin film silicon solar cell.